Picture this, a vast field of golden wheat, swaying gently in the breeze. But beneath the surface lies a hidden revolution, a farming technique that is changing the game for agriculture worldwide. No-till farming isn't just saving soil, it's reshaping our future. Intrigued? You should be. Welcome to the Fields of Innovation YouTube channel. Smart farming starts here. Discover the future of agriculture, where we share information about technology applied in agriculture. No-till farming represents a fundamental shift in how we approach agriculture. Instead of fighting against nature through repeated mechanical disturbance, farmers are now working in harmony with soil biology and structure. This change has far-reaching effects, from lower fuel consumption to improved water retention and increased resilience to extreme weather events. For anyone concerned about rising costs, climate change, or food security, no-till farming offers compelling solutions. Let's quickly compare traditional tillage with no-till methods. Conventional tillage involves physically inverting and pulverizing the soil to prepare a seedbed. In contrast, no-till leaves crop residues on the surface and places seeds with minimal disturbance. The practical differences are striking. Fewer tractor passes, reduced time and labor, visible residue on fields, and some short-term yield trade-offs that farmers need to consider. The benefits of no-till are numerous, including energy savings, reduced machinery wear, improved soil health, and carbon sequestration. However, it's important to note that outcomes can vary depending on soil type, climate, and cropping system. This realistic approach sets reasonable expectations and maintains credibility. So, what exactly is no-till farming? At its core, it's a method of planting crops without plowing or intensive mechanical cultivation. The key principles include minimal soil disturbance, maintaining surface cover through crop residues or cover crops, and diversifying crop rotations to break pest cycles. It's crucial to understand that no-till is not just a single practice, but a comprehensive system. The adoption of no-till has varied across regions and crops. Large dryland cereal systems in parts of North America and Australia were early adopters, driven by concerns over fuel costs and soil erosion. In the UK and parts of Europe, conservation practices were integrated into different crop livestock systems. The socio-economic context, including farm size, subsidy rules, and available extension services, plays a significant role in shaping uptake patterns. No-till farming supports soil structure and ecosystems in fascinating ways. Undisturbed soil aggregates preserve vital pore networks, while fungal hyphae and mycorrhizae remain intact. Surface residues provide food for soil organisms, improving water infiltration, reducing crusting, and allowing roots to explore the soil more effectively. This creates positive feedback loops. Healthier soil retains moisture and nutrients better, which in turn reduces input needs over time. One of the most significant advantages of no-till farming is its potential for energy and fuel savings. Traditional tillage demands multiple tractor passes for primary and secondary tillage, as well as seedbed finishing. Each pass burns diesel, consumes time, and wears down equipment. There are also indirect energy costs to consider, such as manufacturing and maintaining tillage implements and the long-term productivity loss due to increased soil erosion. No-till dramatically reduces energy use by cutting the number of field operations. Fewer passes for plowing and harrowing translate to lower direct fuel consumption. This reduction in mechanical work also means less labor hours and lower equipment maintenance costs. However, it's important to note that fuel and energy savings can vary significantly depending on the crop, machinery, and how fully the system is implemented. When considering the net energy picture, it's crucial to look at the overall balance. Compare the fuel saved against any new inputs required, such as increased herbicide application or specialized seeding equipment. Over multiple years, many no-till systems show improved energy efficiency as the benefits of fewer passes and better soil functioning compound. The environmental benefits of no-till farming are substantial. By protecting the soil surface with crop residues, no-till significantly reduces runoff and topsoil loss during heavy rains. These residues act like a protective mulch, slowing raindrops and stabilizing soil aggregates. This not only prevents erosion but also increases organic matter content and water retention in the soil. Undisturbed soils accumulate organic matter more effectively, which increases the soil's water-holding capacity and resilience during drought periods. This has direct economic benefits for farmers, potentially reducing irrigation needs and improving crop establishment under stressful conditions. No-till farming also contributes to carbon sequestration and climate mitigation. By leaving organic material on the surface, rather than rapidly oxidizing it through tillage, no-till can increase surface soil carbon compared to intensive tillage practices. However, it's important to be transparent about the variability in sequestration rates based on climate, crop type, and management practices. The reduction in soil disturbance and retention of residues tends to increase soil fauna, such as earthworms and beneficial insects. When paired with habitat practices, no-till can also support above-ground biodiversity, including pollinators and beneficial predators. Implementing no-till farming requires specialized equipment and tools. Planters and seed drills designed for no-till must be able to place seeds through residue and into firm soil. This often involves disc or coulter systems to cut through residue, and seed openers that ensure good seed-soil contact without deep cultivation. Matching seeder design to residue load and soil moisture is critical for success. Residue management tools like choppers, row cleaners, and specialized attachments help avoid issues like hairpinning and ensure consistent planting depth. These practical details are crucial for farmers, as poor residue handling can lead to poor crop emergence. Precision agriculture technologies integrate well with no-till systems. GPS guidance, variable rate application, and sensor feedback can reduce redundant trips and optimize input use. For example, precision seeding reduces overlap and saves fuel by ensuring coverage with fewer passes. These technologies also improve decision timing, which is often more critical than raw horsepower in farming operations. When considering technology adoption, it's important to note that new equipment can be expensive. Farmers might consider options like equipment rental, contractor services, or phased purchases as practical pathways to implementation. Real-world case studies provide valuable insights into no-till adoption. When analyzing these studies, look for before and after fuel bills or fuel use per hectare, interviews about the learning curve, and visual footage of field operations. Pay attention to the farmer's strategy for weed control, residue management, and how they measured savings. It's crucial to consider regional variations in these case studies. Examples should reflect different target markets, from large cereal operations in Canada and Australia to mixed farms in parts of the US, and smaller fields or specialized rotations in the UK. Climate and crop choice significantly affect results, but some lessons can be generalized across contexts. Key metrics to report in these studies include fuel use per hectare, number of field passes, input costs for fertilizer and herbicides, yield trends over multiple seasons, and soil health indicators like organic matter content and infiltration rate. Multi-year tracking is essential, as single-year results can be misleading. While no-till offers many benefits, it also comes with challenges. Weed management and potential increased herbicide dependence is a common concern, especially in the early transition years. Farmers often need to develop integrated strategies, including targeted herbicide use, cover crops for weed suppression, stale seedbeds, and spot cultivation where necessary. Emphasizing resistance management by rotating herbicide modes of action is crucial. Transition costs and knowledge gaps can be significant barriers. Solutions include phased adoption, using contractors, accessing government cost-share programs, and engaging in peer-to-peer learning through extension services or farmer networks. Nutrient stratification and residue effects require careful management. With minimal mixing, nutrients may concentrate near the surface, potentially affecting seedling uptake in some crops. Mitigation strategies include using starter fertilizers, banding, or nutrient injection systems, as well as incorporating cover crops and diverse root systems that help redistribute nutrients. Compaction and traffic management are ongoing concerns in no-till systems. Repeated traffic lanes can lead to compaction, but solutions like controlled traffic farming, occasional strategic deep ripping, and attention to axle loads and tire pressures can help address these issues. Pest and disease dynamics may shift with reduced soil disturbance. Implementing integrated pest management, IPM, diverse crop rotations, biological controls, and regular monitoring allows farmers to adapt their strategies over time. In conclusion, no-till farming is a systems approach that offers significant energy and environmental benefits. However, outcomes depend on local context and adoption strategy. It's best viewed as an investment in soil capital, with benefits that generally grow over multiple seasons. For those interested in exploring no-till, practical next steps include starting with trial strips, prioritizing good residue, managing seeding equipment, integrating cover crops and rotations, and tracking fuel and soil metrics to quantify benefits. Remember, the transition to no-till is an iterative process. Expect realistic outcomes. Focus on the economic and climate co-benefits, and don't hesitate to seek out detailed examples or region-specific data. By embracing these energy-saving techniques, we're cultivating not just crops, but a more sustainable agricultural future. Thank you for joining us on the Fields of Innovation channel, where smart farming starts and the future of agriculture unfolds before our eyes.